Hi everyone, my name is Marcel and I'm about to tell you about our recent work on single copy stabilizer testing. This work can also be found on the archive. Before starting, let me give a quick shout out to my collaborator, Jonas Helsen. Jonas is a PI at the CWI and QSoft in Amsterdam. So I'm gonna be starting out this talk by just trying to explain the title to you. So in particular, I'm going to be focusing on the latter part of the title, stabilizer testing. A natural starting point for that is the subclass of quantum states called stabilizer states. These states are efficiently tractable on classical computers, yet have very important and useful properties that make them relevant for all subfields of quantum information theory, basically. In particular, some prominent applications of stabilizer states can be found in areas such as quantum error correction, classical simulation, and also quantum communication, to name just a few. However, stabilizer states from a mathematical point of view are just +1 eigenstates of a commuting subgroup of Pauli operators. So some states S that fulfill this eigenvalue equation here simultaneously for a group of Pauli operators that is usually called the stabilizer group. And in particular, in this talk, whenever I say stabilizer state, I mean pure states. Now, stabilizer states are not universal. They lack a resource that is called magic, which is a fancy word for saying non-stabilizerness. In particular, it's well known that supplementing stabilizer operations with magic, with this resource, yields universal quantum commutation. From that point of view, magic can be seen really as a resource that can be studied from a resource theoretic point of view, similar to how we study entanglement. One thing we would then like to do is quantify magic. So in this talk, I'm going to be focusing on a very simple way of quantifying magic, which has a nice geometric picture associated to it. In particular, let's stop n denote the set of all n-qubit stabilizer states. Then I'm going to define the magic of a quantum state psi just as the distance from the set. And here distance, because we're talking about pure states, is measured in terms of infidelity. So this already brings me to the task of stabilizer testing. In particular, this task takes as input identical copies of some unknown state psi, and the goal is to decide between two cases. Case 1 is psi is a stabilizer state, and case 2 is psi is at least epsilon far from all stabilizer states. So if you recall what I just told you about magic, then in words, this testing task is essentially about detecting the presence of at least a non-trivial amount of magic in an unknown quantum state. Now, this task also fits into a framework that's called quantum property testing, which is a quantum analog of classical property testing, where the object to be tested is now a quantum state ρ. In general, in quantum property testing tasks, we would like to construct some testing algorithm, which consists of basically a measurement schedule and some classical post-processing, and takes as input a quantum state ρ, or rather many identical copies of it. Here I've put the number of copies to be t for concreteness. And then after running the testing algorithm, it should come up with a prediction for whether the state ρ has the property that we're interested in or doesn't. Now, as usual, we would like to study the complexity of this task, in particular in terms of time complexity, which measures the runtime of this algorithm, including both the quantum gate complexity, but also the runtime of the classical post-processing, and the sample complexity, which is the number of copies t required here in order to get a good prediction with high probability. Now, hopefully this explains the stabilizer testing part of the title. Let's focus then on the single copy part. So to understand the distinction between single and multi-copy algorithms, we have to sort of zoom into this box here that I've called the quantum testing algorithm and explain a bit more what's going on inside. So a single copy algorithm is one testing algorithm, in our case, that operates as follows. It takes the first copy of the state to be tested and makes a measurement on it in order to obtain some outcome x1. Then, maybe after some post-processing, it decides on another measurement m2 and applies it to one new fresh copy in order to obtain a measurement outcome x2, and so on and so forth. Crucially here, the algorithm always operates on only a single copy at a time. But that's not the most general thing that you could consider. In particular, you could also consider something like this, where now we're making measurements jointly on two copies at a time. And in general, the most general thing that you could consider is making one big entangled joint measurement on all available T copies at the same time. Now, these algorithms here on the right are called multi-copy algorithms, whereas these algorithms here on the left, the more restricted ones, are called single copy algorithms. Why does this distinction matter? Well, the single copy algorithms from a practical point of view of having to implement the algorithm, these algorithms are deemed the most feasible, whereas making a huge, big entangled measurement on all T copies at the same time is usually infeasible. So in particular, this distinction of looking at how many copies your algorithm operates on at a time is sort of also provides you with a hierarchy of feasibility. Now, restricting your attention to single copy algorithms also often comes at a cost. In particular, many previous works already have shown sample complexity separations like the following. Let's look at the example of purity testing. Purity testing is somewhat similar to stabilizer testing, but instead of stabilizerness, we're testing for purity. So we're testing if some input state psi is either pure state or the maximally mixed state. Then it's been shown before that single copy algorithms require an exponential amount of copies for this task, whereas a simple swap test that can be done by a two copy algorithm, so a multi-copy algorithm, can achieve purity testing with constant sample complexity. Another example for such a separation is Pauli shadow tomography, in case you're familiar with that. And these two separations have been shown in this paper below here, which I think is a very nice reference to get started on this topic and understanding some of the techniques. Now, this brings me to our results. We studied the task of single copy stabilizer testing. So stabilizer testing under the restriction to single copy algorithms. We proved two complementary results. Our first result is an upper bound. In particular, we show that there exists a single copy algorithm for stabilizer testing that uses a linear amount of copies and runs in cubic time so efficiently. Our second result is complementary. In fact, we show that any single copy algorithm for stabilizer testing must use at least square root of n amount of copies. So in particular, if you take these two results together, then you can see that we somewhat characterize the sample complexity. In particular, it has to lie asymptotically in the regime between asymptotically square root of n copies and linear number of copies. Now, this sample complexity separation also gives rise to a separation. Namely, in previous work by Gross, Netzami, and Walter, it's been shown that if you have access to two copies at the same time, then you can do stabilizer testing with a sample complexity that is independent of the number of qubits. In our work, we show that in the single copy case, there is a dependence on the number of qubits. However, if you compare this separation to what I showed you previously, the separation is not quite as huge. It's a bit more fine-grained. Now, in the rest of the talk, I'd like to explain to you the ideas both behind the algorithm, so the upper bound, and the lower bound. So how we prove these. Let's first start with the algorithm. The algorithm itself is actually quite simple. Let psi be the unknown state. Then we sample once a random Clifford C, apply it to the state, and then measure in the computational basis to obtain some measurement outcome x1. Now in the algorithm, we don't do this only once, but many times to accumulate samples from this measurement routine. Here C is always the same Clifford that we sampled once randomly at the beginning. Now, the key idea behind the algorithm is to check for linear dependencies within these measurement outcomes. So in particular, let's assume that we took in total k samples, where k is bigger than n, but still of the order of n. And then let's look at the probability that the span of these samples is the full binary n-dimensional vector space. So if we look at this probability, then if we assume that psi is a stabilizer state, we show in the paper that you can exactly calculate this probability. In particular, for stabilizer states, if n is sufficiently large, this probability converges to roughly 0.42. On the other hand, we also show, and this takes quite some work, that if your state is at least a bit away from the set of all stabilizer states, then this probability is always also a bit larger than 0.42. So the idea of the algorithm is now that we can simply estimate this probability by sampling a bunch of times, and therefore we have a way of detecting this gap whenever the state is a non-stabilizer state. Okay. This was the algorithm. Now let's come to the lower bound. So for the lower bound, we first observe that we can reduce the task of stabilizer testing to a simpler problem where instead of testing stabilizer states against any non-stabilizer states, we now test uniformly random stabilizer states only against the maximally mixed state. And we can easily show that if you can prove a lower bound for this problem, for the simpler distinguishing task, then this lower bound also immediately translates to a lower bound on stabilizer testing. Okay, now formally speaking, we formulate this distinguishing task as a t-copy distinguishing task, which is the following problem. You ought to give a two-outcome POVM mi minus m, that distinguishes with probability at least 2/3 between these two states. The state 1 here is the uniform mixture of all t-copy stabilizer states, and the state 2 is the t-copy maximally mixed state. So this problem formalizes the distinguishing task that I had just mentioned, and it's sort of implicitly dependent on t. Now, how do we prove a lower bound for this task? Well, we can simply look at the bias of any given POVM, two-outcome POVM M, which is given by this quantity below here. It's basically the probability that the POVM can discriminate between case 1 and case 2. And now our goal to prove a lower bound is to bound this bias, so to show that it is small unless t is sufficiently large. And if the bias is too small, then the test automatically cannot distinguish between these two cases, the probability 2/3. Okay, so how do we bound the bias? I won't go into the details, but I will only touch on the main ingredients. The first main ingredient that comes into this is to realize that there's a big symmetry in stabilizer testing and also this distinguishing task that I just mentioned. Namely, the optimal test can be assumed without loss of generality to be Clifford invariant. So formally that means that it lives in the commutant of the Clifford tensor powers. This is this set com and t here. And the set is formally defined as all linear operators that commute simultaneously with the tensor powers of all Clifford operators. Okay, this set is a vector space actually, and it's been studied and characterized to great extent in this paper by David Gross, Stepan Netzami, and Michael Walter from 2017 that I already mentioned earlier. And among other things, they show that the dimension of the space is actually quite low in the regime that we care about. In particular, it only depends on t. And intuitively, this means that we can already restrict massively the set of POVMs, so tests, that we have to consider. So this is one big help. The other thing is, of course, that we have to make use somehow of the single copy assumption. Otherwise, we're just going to reproduce the bounds that were already known for the multi-copy case before. And the way that we do it is inspired by this paper by Harrow from 2023, who shows a similar bound to ours, a similar lower bound, for the task of purity testing instead of stabilizer testing. And he realizes that the single copy algorithms, they are generalized by algorithms that can be mathematically constrained by the PPT condition. So the PPT condition for the two outcome POVM that we're interested in is this condition below here. It just means that all the partial transposes for all subsets of the T copies, denoted like this, are also positive. Okay. And then combining these two ingredients, we're able to prove this lower bound by studying partial transposes of operators that live in the commutant. Okay, now let me wrap up. We studied the task of stabilizer testing, which is the task of detecting the non-trivial presence of magic in a quantum state. But we studied this under the restriction to single copy access only. And our main result is the sample complexity characterization that says that the sample complexity of this task lies somewhere in between square root of n and linear amount of copies necessary. Now, in terms of open questions, of course, the most immediate open question is to close this gap in the sample complexity. And then a little bit more broader, it would also be nice to see if instead of just testing for magic, there was a way to estimate magic efficiently with single copy access. In the case of multi-copy access, there are some protocols already known for estimating magic, but not with single copy. Okay, this brings me to the end of my talk. Thank you very much for listening.